Hey guys, this is Chen. Today is our art section 3. So today's purpose is to running the rating scale model with RStudio. It's different from the dichotomous Rasch model. So besides the item and person estimates, we can also find the information about all the thresholds throughout the items. So let's start it by review the for equations, model equations. So that's exactly the same with our R Rasch book. So you can find the same information in our Rasch R book. And I will also attach the R book link to this video, so you can just click the link below that video, so you will find a quick hyperlink to our R book. So in here, this is the equation of our rating scale model. So we have the theta as the personability and the delta as the item difficulty. So these two are basically the dichotomous Rasch model's components. So the new parameter here is actually this tau. So this tau is pretty much the thresholds. So in here, we just put the thresholds in our equation as a variable. And the RSM, which is the rating scale model, assumes that the threshold structure is fixed across items. So that means the relative distance between the thresholds is the same across the items. Okay, so let's start our example. So first of all, we library all the packages. And I just hit the Command plus Enter. That's basically the same thing when you select this code and click in here. You can see the short key is in here, the hot key, whenever it called. So this is a faster way. And also you can see whenever there's a command, it might have some hotkey labeled in here. So you can always use the hotkey if you really know well with all the RStudio functions. And then let's library the TAN. That's for running our rating scale Rasch model. The read R is for importing the data, because in here, in today's lab, we're going to import the CSV, so we need to read R package. And then we use the plyr plot function, plot package for plot the item characteristics curves. And also we need the right map to plot the variable map. And also today we provided you two different examples, one with the ERM package and one with the TAN package. So by comparing these two packages functions, you can see like what is the differences in their functions, expressions, and even the results. Okay, so let's understand our data first. So in here we use the bronze data. Let's just use this B data. So in this analysis, so the original data set includes ratings for 32 students by 12 readers on 3 separate essay compositions. So for this lab, we will look at the data from essay 1. So it just all the ratings is for essay 1. For ease of interpretation, the essay ratings from the original dataset have been recorded from 9 categories to 3. So in here, we only have 3 categories. 1 means low achievement, 2 means middle, and 3 means high. And in here, we assume that the distance from low to middle is pretty much the same from middle to high, right? Okay, so in our analysis, we will treat 12 readers as 12 polynomous items that share the 3 category rating structure. Because basically, one student has 12 readers rating one essay. So basically, we can regard these 12 raters as our 12 items. Okay, so let's get our data prepared in here. So we just put the B data in here and call the read.csv function. I just click the commander and plus enter. So I run select lines. Okay, so I won't say that a third time, but I think that's enough. Okay, so let's see the head of the data. So when you call the head function, it always prints out the first 6 rows of the data. So you can see in here, so we have rater 1 through rater 12. And also, we have the first column as student's ID, right? But another way to review your data is simply click the data on your right side in here. So basically, you can see all the data in here, and also you can order them by their columns. For rater 1, 1 is the minimum and 3 is the maximum. And for rater 1, there's only 1, 3, right? And also, there is a quick tips in here, so you can, when you click the flitter, so you can see the distribution. This is the student's distribution. 30, these are the 30s and these are the 5s, 5 students. And in here, rater 1, we have 1, 2, 3. You see, the rater 1 only have 1, 3 in here. So he gives a lot of 1 and 2. Mostly it's 2, but just 1, 3. So we can tell that, because 3 is high achievement. So we can tell that a rater 1 is kind of a severe rater, right? Then we saw the rater 2, and rater 2 is kind of interesting because he never used he or she never used the third category. He only used the first and second. So you can basically check every rater's distribution, the rating distribution here, and you should have like a general ideas like how severe this rating, or if like a rater always use the second category, that means he is always trying to give like a neutral assessment. Okay, so let's go back to our data, and we can summarize the data in here. So the reason we do summarize the data every time is we want to check whether there is a missing value. Because in here, this is such a really small data. You can see all the data like in couple seconds. But if it's like a huge data set, you really need to call the summary on this data so you can see whether there is a missing value here. So in here, rater 1, the minimum 1, maximum 3, rater 2, minimum 1, maximum is 2. And there's no NAs, which is the missing values. There's no missing values, which is good, right? And also when we check the mean, so the higher the mean, which means the raters can give students like a really high score, which also means this rater is a linear rater, right? If the rater's mean is like the lowest, which means this rater is the severest rater. Okay, so we need to train the data first, because every time when we run, whenever rating scale model, partial credit model, or dichotomous model, we need a response matrix. For the response matrix, when you compare it here, so the only column that we don't need is the student ID. In here, we just take the comma. Anything before the comma means rows, so it's empty because we want to take all the rows. So in here, the -1 means we don't want the first column, so we just take out of the first column. Okay, so let's run this code. Okay, so now we have this rating scale data ready. Okay, so here is the B data set without the first column. So this is good for us to run the model. Okay, so here we're starting to run the model by call the TAM-MML function. So, and we setting the IRT model to rating scale model as an argument, as the second argument in here. Okay, so now it shows you the iterations in here. Okay, it's done, and so when you finish the first run of your model, so it gives you the estimation for all the raters, which is all the items. So if you regarded raters as the items, so basically these estimations are item difficulties. So let's check rater 4. Rater 4 in here. You see, rater 4 only gives 1, 1. And then all the students like 2 or 3. So rater 4 is really lenient. So the lower the value means the more lenient the rater is, and the higher the highest value always means like the most severe rater. So let's summarize the model in here. So basically you can have all the raters beta, and with here is the new things like different with our dichotomous models outputs. So here gives you the tau, which is the categories location. So for each item, besides a total location on logistic scale, it also gives you 3 different. In here is 3 for the first item. For the first rater is 3, but you do remember for rater 2, since he only used the category 1 and the category 2, so we don't have category 3's tau in here. Please note that the first example is the TAM package. So if you are going to use the ERM package, you need to make sure all the category has been used. So this is the differences in the presettings for each package. So in the ERM package, ask you all the items supposed to use all the categories. If you are not using all the categories, the system will, like the R will throw you an error. But the TAM package is like more tolerance on these missing categories. So we are okay, we are fine in the TAM. And that happens because sometimes we only have like a really small data set and we use so many categories. So that's why like not all the category has been used by all the items and by all the raters. In this case, you need to consider to use a partial credit model instead of the rating scale model. So the ERM package, since it applies a relatively strict rule, so it did not accept this dataset for running the rating scale model because the relative distance for each item is not the same. In here, you can see the rater 2, the item for rater 2 is the distance, the relatively category distance is different with the others. Okay, so let's do a right map here. Since we have already, here, please note this function. Some people just report me that they might not be able to run the plots. So this is the way to solve that question, and the reason it might lead to that question is when you run your RStudio, you might use some plots, and like the plots location might have some kind of conflicting with the new plots location. So this is, we put the graphics off, and then when it's when you call it the new plotting function, it will grace a new plot here. But like I think most of you might not have this problem. But if you have this problem, it gives you some error message. So try this function. Okay, try this function before you contact me. And then you're supposed to run your right map correctly in here. So in here we have the right map. It shows you 12 raters, and on the right side is the logit scales from 0 to -10, which means this test is kind of easy, and like not a test because it's raters in here. So like, which means the most raters are kind of linear, right? And the category 3, probably I think it's only the category 3 is like above than 0. So which means only the category 3 might be a little bit higher than our subjects. So mean you can tell like pretty much our subjects' main ability is in here. So this is the distribution of our subjects, right? So most students should have at least a category 2. Only a few really like several students might have category 1. Okay, and then we can plot our expected response curves. I'm sorry. In here, the argument ask equals to false means I just plot all the plots at the same time. But like if you choose true, so the systems will plot the plots one by one. So you need to hit the enters. So in here, I just want to have all the plots at the same time. So I just click that. So the blue line is the expected score curve. So pretty much for rater 1, if a student is if a student have like abilities on -2, the expected score for rater 2 for rater 1 will give you is around like 1 to 1.5, right? So this is something, and this is the real data set. So if this the real the blue line is close to the black line, which means like our models fit the data, right? And you will see some raters have like in here these two a little bit abbreviate from our expected curve. Okay, and but like most of all, when you check all the plots, like most rater 4 is really good rater because like his expected score curve is almost the same score with our the real data, right? And this one is like the persons with like the moderate ability is pretty much the same, but like if the person have like a really high ability, so the raters kind of give you even higher grading, and vice versa, right? So pretty much that's everything we can check for the raters. And if like your expected line is totally, it's like if there is something if the expected score curve and it's totally abbreviate, it's like you can see a huge abbreviate from your the real data. So which means there's something wrong with this rater, or if it's a test item, you should see like that might be something wrong with the test item design. So that's where you go back to double check the items to see like what's wrong with the items. Okay, so let's run the item characteristics curves. You see, I got this arrow now. So whenever you got these arrows, it means like the system cannot open the file which is already there. So the way to solve that is just run this function again. Okay, so when you run this function, you are able to run the plots. Okay, now we have the ICC, which is the item characteristics curves. So let's check the ICC. You will find there are one more categories, right? Remember, for item 1, we're supposed to have 3 categories, but in here it's 4. So the category 4 actually is the the category 4 actually is the overall for this item, for this rater. So, and you can see the last category is always like from this direction, which means if you have like higher ability, you have more chance to get this item correct, right? You can, and let's check the Radar 2, because the Radar 2 only, do you remember the Radar 2 only used the 2 categories, which means the category 3 is the overall curve for item for Radar 2. It's the same direction, right? And in here you can see, like, among all these ICCs, you can see almost every plot, the category 1 is a line, right? Is a horizontal line. That means like under most of the situations, this category 1 has no change, has no variance. So that means like if you have like an item design and you have category 1 like always like that, so you probably need to consider, is it necessary to have a category 1 like that? Because like it feels like not everyone use the category 1, and the category 1 is like not really important in here. But like when you check the category 4, which is like the general one, so you should see some curves like that, and which is good. And you can see all the curves, like most of the curves in here. You see the abilities from -2 to 2 in here, might be 3 in here. But when you check the ability, student's ability is 0.7. So it's pretty much like if a student have a relatively low ability, like in here is 0.4, he can get this item correct. He has a really high chance, like 100% chance in here, right? That's pretty much the same. And let's go check the item estimates. So since we already ran the model, and this is our model, and it has different lists, it's a model with a different lists. So it has 57 lists. So each list containing some different informations for our results. So in here, we need to use the $sign to call the parameters that we need. So in here, we use the RS model $sign XXI. So the XSI actually is the item estimates. So this is the item difficulty. In this case, it's rating severity. So when you run that, it got the power, the thing again. So remember, we just need to use the graphic off function and run it one more time to clean our memory for the graphic, and then we can plot our, we can run the function. We can run the function without any arrows. And then we can see this is the standard arrow for our estimates, and this is the estimates for the radars. And in here, since you got this line, so if we can, let me show you something. So we can actually store that table if we use like the radar estimates. And the reason we are doing that is sometimes you just cannot see those, because it's not like it's ordered by these radar IDs. Okay, and we have a general category IDs for category 1 and 2. And in here, we can just click that, and you see the category 1 is the easiest one, so it's like the lower risk. but we want to see like the differences between these raters. So we can tell like the rater 4 has the lowest score, lowest value, which means the rater 4 is the most lenient rater, and the rater 8 is still a negative, which means rater's severity is slightly lower than student's ability, if the student's ability is 0, right? Yeah, because like when we check the right map, so we can tell like the pretty much the student's mean abilities should be above 0, right? So even the most severe rater still a little like slightly lower than the student's overall ability. Okay, and then we can just use the fit to get all the fit statistics. We can use the TAM fit function. Now you have the outfit and the infit and the t value and p value. Okay, so when you check the outfit, as it pretty much applies the same rules like we just discussed in the previous lab. So we expected these values are like close to 1. If that's close to 1, so that's okay. But if it's like rater 10, his outfit is a little bit lower, and right, his outfit is kind of lower. And also for rater, I think it's rater 1, his outfit and infit is also lower. So when you go back to check the rater 1, you might find something like he might rater some specific student with like higher score. That means and also it could be happen like if because outfit means like something doing something, some subjects doing something that really should not happen, right? But in here, the rater 1 outfit is kind of low, which means the rater 1 might give a student with a low ability a really high score. So that's could happen. So and this is some kind of clue for you to go back to your raw data to see what's wrong with this rater's rating on one specific student, right? Okay, and then we can use the TAMWLE function to get the person ability. On the previous, we got all the items, right? These are the raters, and at the same time it's the items because we regarded these raters as items. So let me rephrase that. From every, I think almost every, from every Rasch model results, we have like 3 chunks of information we are going to looking for. So the first one is the item, anything concerning the item estimates, item difficulty, and item fit statistics. So the first chunk is item. The second chunk is the subjects, all the text takers or the participants, right? So in here, in most of the situation, it could be students. So the second chunk is the students' information. So it concerning like the person abilities, like the person fit, like the person infit, outfit, something like that. And always we have a third trunk. The third trunk is like all the different plots, like the item characteristics curve, like the expected response curve, and the most important thing is the item person map, or the right map, or the variable map, whatever it calls. It have like several different callings, but like it basically referring like the same thing, right? So for all the Rasch analysis, we should have these 3 different chunks of information that we are provided to let's say if we are doing a article, so we must report these 3 different chunks of information in our publication. Okay, so let's check the person abilities in here. Here, so you can have the all the estimates stored in your person ability in here. We can check that by just simply click that. So this is the every person finish all the 12 items, and this is the person score, person max. So this is the like let's say student 1, he got 29 out of 35, right? And this is the theta. Actually, this is the estimate. This is the location that that indicates the person's ability, right? If we list it here, so we can tell that the person 24, the ID 24 student, has the lowest theta. He has the lower risk academic achievement, right? If the student 19 has the highest theta, which means student 19 has the highest student achievement, and he got 29 out of 35. And our first person, you see, only got like 15 out of 35. Okay, so let's print out the theta. I use the hand just to show you this 6, but since we only have 33 observations, so it's okay to just click the data set, right? And we use the TAM person fit function to get the person fit, and I store that in RS person fit underscore person fit, and then we can check the. Actually, I think it's not a really big table, so let's just go back to in here to see. So now you have like 32 students outfit and infit, and an easy way, just click on that to see like where is the lower risk. Like this person is really has like way lower than 1, right? And the infit is also way lower than 1. So these are the outliers that you're supposed to go back to your raw data to see like what happens to these students, why this student has like such lower outfit. So usually the lower infit or outfit statistics, that means that there is like more consistency in responses comparing to the expected data by the model. So if you check these 6 students, you might find like this infit and outfit is kind of low, which means like they keep doing like the same category, they keep using the same categories, right? This and also when you check, you see like the highest, like these 3, I guess. So when you go back to your data, you might go back to see like what happens to those outliers. Okay, so let's go back and okay, since I've shows you all the plots, right, map plots, expected response curves and item characteristic curves. This is the third trunk actually, and then this is all the information about item estimates and the fit statistics, and then this is the third trunk as the second trunk as the person estimates and the fit statistics. So basically for each trial you need to have these 3 trunks of different informations as the result. So in here I give you another example with the ERM package. So the ERM package also provides functions to run a Platonymous Rasch model. So in this function, we just use like a built-in data set to show you how to run the Rasch rating scale model. So in here, by loaded the data set, we use the data function and call the name of that data. So when you run that line, so you should have data RSM data loaded. So let's see where is our data. Okay, RSM data is loaded, and let's summarize this data function. So once we summarize this data function, it shows you the data is in here. So basically, it's just it without the first column, which is the student ID, and this is the pure response matrix through item 1 to item 6. Right. So these data include 20 participants' responses to 6 items that included 4 ordered categories. So in here, which is different with the previous case, is all the items used from 0 to 3. And when you check in here, the minimum 0, maximum 3, 0, 3, 0, 3, 0, 3, 0, 3, 0, 3, which means all these students used all the categories, right? Not all the students, not all the raters used all the categories. So note that in the summary of the RSM data objects, there are response in all 4 categories for all items. So this means that it is possible to run the rating scale model on this item response. So if participant did not use all the categories on all of the items, then we should need to run the partial credit model instead. Okay, so you still can run the model with TAM, but you need to use the partial credit model. Otherwise, if you stick on the rating scale model in the TAM, so the TAM package is gonna throw you an error. But in here, the ERM function is much friendly to those missing categories. Okay, so let's use the RSM function, which is the abbreviation for rating scale model, to run the RS model. And then we have 2 easy functions to the thresholds to get the item estimates. So once we get the item estimates, you should see for these 6 items, we have the logit location for each item, and also we have different logit locations for each thresholds. So, and also you need to notice that when you add up, sum up these threshold values, it's supposed to be 0. Okay, and then let's get the threshold as standard error. So pretty much they save these values on the item estimates $SE the thresholds. So once you got the thresholds, so you have different standard errors for these different thresholds. And then we have the person part. The person part is the CDAR, so we use the person dot parameter functions to get the person locations. You can also see the standard and then arrows, we use the summary to see their person. So we have 12. And then 20, let's check the item and person fit. So it's also very simple by call the item fit on the person location estimates. This is please note that they save all the informations in the person locations estimates. So when you check here, person location estimates is a list of 18. So a bunch of information stored there. So you use another function to get the item fit. So and you also use the person fit to get the person fit. So let's check the item fit first. So now you can see the different outfit and infit for these items. And when you check the value, outfit MSQ and infit MSQ, you should find they are pretty much all close to 1, which is kind of good. And there's no really significant p-values in here. So which means the data and models, the data sort of fit the model. Okay, and then we check the person. The person outfit infitting here, and this one might have a little bit problems, second person, because his fit and all the in fit is kind of a little bit lower. And this one's outfit might have some problems. Oh, and this one, right? So, and when you check the p-value in here, sometimes it's something wrong. It's like you can see it's like less than 0.05, which means something's like the infitted outfit is something wrong. And sometimes on the opposite, if it's like really close to 1, if it's a really high number, it still indicates something's wrong. Okay, so you in here you are not just looking for something like less than 0.05, and I just observed that if something's outfit infit is like a little bit abnormal, so this p-value could be high. This p-value could be close to 1. So if the p-value close to 1, sometimes it's 1 means you are not good. This person is not good. Okay, so you need to go back to your data to see like what's wrong with this person. Okay. And okay, so let's do the person item map. So in here, this is the person item map. That's pretty much the same thing with the right map I just show you, but the style, like the presenting style, is different. In here we can see, and this is something should not supposed to be happen. In here we're supposed to see the category as ordered like 1, 2, 3, 1, 2, 3, but in here it's 2, 1, 3. So that means if the category has its own location in here, this is the location on the logistic scale. So which means the category 2, like for item 6, the category 2 is easier than the category 1. Okay, so that's if it's consistent like this, like all is 2, 1, 3, 2, 1, 3, 2, 1, 3. That means like you may be you might be mistakenly order the item, right? Also, it also could be something like yes and no, if you have some attitude questionnaire, right? And then one is agree and disagree. Sometimes like the 0 in like the midpoint in here is don't know, but you will know like don't know is if you cannot put like a don't know and with yes and no on a ordinal scale, because don't know is not supposed to be in the middle in between the yes and no, right? So that's something like you need to consider about your test design. So when you run the rating scale models, your category is supposed to be somewhat continuous or ordinal, right? If that is not ordinal, and like you always have like disordered category numbers, like if it's all different, like in here is 2, 1, 3 and in here is 3, 1, 2, so that means you might have something wrong with your item design with these categories. Okay, and then let's plot the standardized residuals. We still use like the same function code, like the code chunk here, which we used. That's thanks Dr. Wayne for creating this nicely plots. And in here, this code is trying to get the standardized residuals from the item fit. And then we save that to the standardized residual. So when you check the here, so this here, we saved that all the standardized residuals in here. And when we run, we need to take out the maximum. We also need to get the minimum as the maximum residual and the minimum residual. And then since we have the maximum and the minimum, then we need to find the -2 and the +2 as standard deviations. And then that's the line we got. Let's get that plot out first. Okay, we plot out that. So basically, we are looking for the outliers out from the, and in here it's supposed to be have another red line as the -2, but there's no persons like in here. So that's why like this plot only shows you those parts. Okay, so that means we are safe. And when we check all the plots, you see all these observations are like inside the -2 to +2 standard deviations range, right? And in here, for item 2, we have only one outliers. So that's acceptable. And for others, I don't see any outliers. Yeah, so which means like pretty much almost everyone for all the items like lie in these standardized residuals from -2 to +2 standard deviations. That's good. So let's plot the in empirical IRF item response functions. This is the IRF, and that's pretty much is the curve that I showed you for the previous example. It's also the same when you check here. You see the last category is always the general category, like the overall overall curve for this item, right? And this example is much better than the previous example because all the categories has been used differently. See, so we don't have like a straight lies in the bottom, which means we are good. And when you check all the category 3's curve, you will find like a curve like that, which is pretty good. And this is consistent across each plot, which is nice. And if you check the category 0, it's supposed to be like the easiest item, so it's always supposed to be like an opposite direction comparing to your category 3. Okay, so that's pretty much everything for today, and I supposed to have like more learning materials updating in here. So once you see the new Rasch book, so like this Rasch book is keep updating Rasch book. It's a living Rasch book, so I will always put like new things to the Rasch book. So just be noticed that to check your Rasch book anytime, and also I might have some different examples, and you can like go through all these examples to get more familiar with like how to run in the rating scale models in R. Okay, so that's pretty much everything for today. And also starting from this lab, if you might have your own data set and you trying to start with the running the R Rasch model with your own data set, and I'm glad to help you in my R help sessions. By that time, I supposed to put the R help sessions time on that book too, so you can always check what is the available time, so you can log in on the online session on a specific time, and you can get help anytime you need. Okay, so that's pretty much everything for today. Thank you so much for your listening, for your watching, and that's all for today. Yeah, bye bye.